Okay, well, I was hoping to be there at the conference, but Greyhound had other plans for me. So I'm going to be presenting from Purdue here. So good afternoon, everyone. My name is Sanjeet Suhag. I am a senior studying computer science and physics at Purdue. And I also work as a simulation programmer here at the Envision Center at Purdue. And a lot of our work deals with creating data-driven visualizations and simulations. I'm going to be talking to you today about a project called Flight Profiler, which is mainly focused on generating and displaying 3D volumetric weather for the purposes of flight planning. So for this project, we have been collaborating with the FAA and employing new data processing and rendering technology on weather data that is publicly available from sources such as the National Centers for Environmental Prediction. I'll be shedding some light on how we're trying to help solve, with visualization, a pretty pervasive problem in aviation circles through just a new method of visualizing and, more importantly, interacting with weather data. I'll be talking about some mistakes we made in the process, some of the lessons we learned, and a few general insights regarding dealing with very large data sets and trying to efficiently visualize millions of data points on a web platform. So the original problem statement for this project is as follows. A segment of the general aviation population gets into unsafe situations. The FAA has not been able to decrease the incidence rates. So the objective here is to create a toolkit to show these danger zones. So let's dig into that statement a little bit. What do we mean by general aviation? General aviation is concerned with private or recreational flying, as opposed to commercial and military. So these aircraft that we're talking about, they're single-engined, your Cessna 152s, 172s. And these aircraft are typically not geared to fly in most weather conditions, in all weather conditions. By unsafe situations, we mean conditions that a pilot may not be rated or trained for. In aviation, there are certain categories for weather conditions, and these are defined by the FAA. So VFR, or visual flight rules, apply when a pilot operates an aircraft in weather conditions generally clear enough to allow the pilot to see where their aircraft is going. As opposed to that, IFR, or instrument flight rules, are conditions in which flight by simple outside visual reference is not safe, and flight has to be conducted by reference to your cockpit instruments, and navigation has to be done by electronic signals. So the aim here is to indicate where along a flight path, a VFR pilot may be incurring those IFR conditions. And by toolkit, the idea is to create a pre-flight planning tool to allow a user to enter their flight plan and see what weather they'll be encountering. And at this moment, this technology is strictly for pre-flight planning and not for real-time in-cockpit display. So for this pre-flight planning tool, we wanted to create a real-time 3D picture of the weather. And once we decided on that approach, we had to find ways of implementing it. For practical purposes, we needed this to be an application that runs well on a device like a tablet, since devices like iPads are something that pilots carry around and they're used to it, but we didn't want to be tied into the ecosystem, in the iOS ecosystem. So the only option we had for cross-platform is web. So, okay, we decided we want to do a 3D visualization on the web. So the next step is to decide which web-based GIS platform to use. So we had the option of Google Earth, ArcGIS, or Cesium. We decided to go with Cesium since it was free, it was open source, and it was well documented. However, it wasn't until earlier this year that we found the real benefit of using Cesium, which is its support for a data format called 3D tiles. And we'll get to that in just a minute here, but first I'd like to backtrack a bit and talk about why we decided to pursue 3D. So why 3D? It is clearly a more complex problem. It's going to be more computationally expensive, and most of everything with weather is done on 2D. So for navigation, general aviation uses 2D charts. For their weather planning, they use 2D surface charts. So why 3D? So there are four basic reasons behind our switch to 3D. First is because weather itself is not two-dimensional. Real world weather manifests and changes in 3 dimensions. Second, because the data exists. Organizations such as the NOAA, the National Weather Service, they make available these 3D models for past, current, and forecasted data. So we had the potential to use them. Third, because it's easier for the user to perceive how much clearance they have from weather elements such as clouds when they are looking at it from a 3D perspective. And fourth, it's because it's easier for our flight planning tool to detect collisions between actual 3D volumes. That would be the volume of the cloud and the volume of the flight path. So for a sample flight, let's say Albuquerque to Phoenix, we see the output on the top image, which is from an app called Flight. And Flight is perhaps the most popular app used by individual pilots and professional flight crews to gather weather information in this pre-flight planning phase. And there are other products too, such as the Aviation Weather Center, which is a collaboration between the FAA and the National Weather Service. And they also display their weather elements in 2D. And so on that image, you can see a line drawn out to indicate your flight path. And you see that there are some clouds there, but you can't quite understand how close you are to the clouds. They could be above you, below you. You can't get that information. But in contrast, on the bottom, you see the real-time flight view in Flight Profiler. And we can clearly see the value here when it comes to cloud avoidance. The volumetric clouds are a much better representation of what weather a pilot will be encountering through their flight. So we knew we wanted to generate 3D volumetric clouds from this data set that covers the contiguous United States. And that's an area that covers a little over 8 million square kilometers. And the data set has a pixel size of 3 square kilometers. And that means that in the worst case scenario, if there's a cloud above every single point, we're looking to display just shy of 2 million clouds in a web browser. And in trying to display that amount of data initially, we ran into a wall really fast in terms of performance. So in our rendering engine of choice, Cesium, to draw custom geometry, there are 3 possible methods: entities, primitives, and 3D tiles. So the primitive system is geared towards graphics developers who want to generate custom geometry, while the entity system is a higher level abstraction of that. And it uses primitives, and it's driven more towards data-driven visualization. And for a lot of general geospatial visualization use cases, these systems work just fine. And they're as simple as you can see in the code example, where the entity code is in the red, is in the green, and it's using 2 primitives, a box and a label. But in using the system to try to display 2 million points, we ran into a big problem in terms of performance. And there's three avenues of those problems and why they were caused. So when working with such a large data set, you'll run into a problem with download time, your rendering performance, and display saturation. So let's go through them one by one. So for our weather data that we're working with, each data set is 150 megabytes. And directly downloading all that data is unfeasible, but because our entity system reads that data at runtime and then creates this geometry, that's what we had to do. And we optimized it slightly in the beginning by dividing that data into chunks so the user can slowly see the geometry load in, but it was nowhere where we wanted it to be in terms of performance. Also, mobile devices, in just trying to hold that amount of data, they ran out of memory pretty fast. Regarding rendering performance, on a top spec computer, so that is running an i9-9900K and a GTX 2080, this system ran at 6 frames per second. And that's no fault of the entity system. We were simply using the wrong tool for the job. Such large 3D data sets is not what it's meant to be used for. And regarding display saturation, we wanted some transparency in our clouds to allow the user to see the terrain through them and get a better sense of their location. But we couldn't afford any more performance costs on top of what's being rendered. So we were unable to add that alpha mask to our geometry. And after many futile attempts at optimization, we realized that this existing implementation will never be able to achieve the goals that are set out for this project. So we started from scratch, this time with 3D tiles. And at this time, the 3D tile system was a more mature and tested method of displaying really large data sets in Cesium. So for this new graphic stack that we use, there are 3 fundamental building blocks. The first is GLTF. GLTF is a runtime format for 3D models, and it's what stores our basic mesh data for the basic cube that we use, that is each cloud. It's optimized for efficient transmission and loading. And what that means is that it's designed to get your model data from the disk to the GPU really fast. And leveraging this GLTF format is the 3D tiles format. 3D tiles is an open spec for visualizing and interacting with massive 3D geospatial content. And you can use this 3D tile to combine different types of 3D data, such as point clouds, instance models, batch models, or a combination of any of these. And finally, we chose to stick with Cesium because most of the team behind Cesium were leading contributors to the GLTF and 3D tile spec. And the Cesium engine has great support for 3D tiles. So now at this point, we have our data, we want to convert it to 3D tiles. For most common geospatial data formats, you can use a service called Cesium Ion to convert and host your 3D tile data. However, the data used by Flight Profiler is not directly tileable since it's pure weather information. There's no shapes, there's no geometry. So we had to build our own tiling pipeline to convert this information to geometry, and that geometry then to 3D tiles. So let's look at our raw data that we're working with, the source data. The data set is used, is served in a format called GRIB2, which is a gridded binary format. And the way this works is the GRIB2 data covers some area on the surface of the Earth. So in our case, it's the continental United States. And it covers that area in a 2D spatial grid. And embedded in the GRIB2 file are multiple grids, each representing the value of some weather variable at point XY, since it's a 2D array. And each point XY covers an area of 3 square kilometers in our case. So these discrete grids are called raster bands. And the data set has up to 150 raster bands, one for each different weather element. But for the purpose of generating a volumetric cloud, all we need are the cloud bases and the cloud tops. And then we can start beginning to create our geometry. So to convert it into geometry and to 3D tiles, I'll first give a quick primer into what goes into building a 3D tile. There are 2 core components here. One is called a feature table and the other is called a batch table. A feature table describes the attributes required to render your model. So that would be the position and other appearance properties. And it's used by tile formats. For example, if you're using a batch 3D model, each model would be a feature. If you're using a point cloud, each point would be a feature. In Flight Profiler, we use instance 3D models, since instance 3D model is a format in which you're instancing the same mesh for different features. So we have the same cube, and we're just positioning it and scaling it across the globe. To render them correctly, we simply add the position. The X and Y are dependent on what we get from parsing the 2D array, and the Z, or the altitude, is where the base of the cloud is. And we don't need X and Y scaling because the GLTF cube, the static GLTF cube we're using, is generated to 3 square miles in terms of area, and we simply scale the height by the difference between the cloud top and the cloud base. And that's the basic of the feature table. It gives us enough information to render the clouds. But if you want to get some more data into our 3D tiles, that's when we use the batch table. A batch table contains per feature application-specific properties in a tile. That's essentially metadata. These properties are queried at runtime for styling and any other application-specific use case you might have, such as populating a UI or making a REST API request. For each of these features, so our features are clouds, we assign a batch ID, which is essentially an array index, and we add whatever metadata we want to preserve in the batch table. So these would be information from other raster bands that we want to keep. So for aviation, certain things that would be key are icing, precipitation rate, and lightning. So we have a way to create a tile now, but we have to divide that whole tile set in some way. Otherwise, we're not exactly improving from the original problem, which was getting all that data at once. So how do we choose how many tiles we want to divide our data set into? In my first implementation of this, I simply divided the 2D grid into 16 by 16 chunks, and that worked fine. So instead of downloading the whole 150 megabyte data set at first, the application downloaded only the tiles that were in the current view, and those tiles were only 500 kilobytes in size, and that wasn't much of a problem. But this was a naive approach, and it's not the optimal way of doing things in 3D tiles. So let's talk about how 3D tiles works at runtime and how you should be structuring your data. So tiles are structured in a tree data structure, and it incorporates a hierarchical level of detail. So at runtime, Cesium will need to determine if a tile is sufficiently detailed for rendering, or if the contents of its tile should be refined to its children, which have a high resolution. And that's the equation that we see here. It's a pretty standard LOD algorithm. It's the same that's used in Unity and other engines for calculating screen space error. So that's the amount of overlap two items have, and the overlap is calculated in terms of pixels. So a tile's geometric error defines the selection metric for that tile. Its value would be a non-negative integer that specifies the error in meters that you are willing to tolerate. If the error at runtime is higher than your geometric error, then it will refine the tile to a higher level of detail. And we see an example of that on the right here. On the top is the parent tile, which is these large blocks, and that's a lower level of detail. And past that geometric error, whenever you reach that threshold by zooming into the camera or some other thing, you get a higher level of detail with the smaller blocks. So the root tile of the tree, the root of the tree, being the most simplified version of the geometry, will have the greatest geometric error. And as you go down that tree to the children components, which are the high level of detail, you lower the geometric error. And the leaf tiles, which are the highest level of detail, you want to have a geometric error of close to 0, since you're not willing to tolerate any error there. So now we know that our data is going to be structured in some sort of tree. And for geospatial data, we use spatial data structures or spatial trees. For Flight Profiler, we're dealing with clouds scattered on a surface with varying density. So the approach we now take is to create something like a quad tree, but with tight bounding volumes. So we iterate through the 2D spatial grid, and it keeps track of the bound of each tile. And if there are no bounds, that means there's no cloud. So we just omit the tile, but our tiles are only as big as they need to be. For your data, if you have a more divided data, you might want to use something like a quad tree or a oct tree or even a KD tree. It really depends on the density of your data and how well it's spaced out. Okay, so from this, we know the whole pipeline and how that works and how you'd go about creating one. So let's see about what the results were from doing all this work. So here we see the output from the first entity system. And on a top spec computer, it took 12 seconds for it to load, and the engine ran at 6 frames per second. And this is when we were only showing 25% of the data, which is why the blocks that you see are so large, and they're not true to the 3 square kilometer pixel size of the original data set. But when we switch to 3D tiles, we see we get a much better result. We were instantly loading it in 0.75 seconds, and we were achieving 50 FPS on an iPad Air. And that's a huge improvement, especially given the fact that we're now rendering the data at the full resolution. So in the coming slides, I'm just going to show you a close-up view of what this volumetric weather looks like. So you can see how you would pan around the globe and see what the actual clouds would look like as they move along the surface. Now, as far as the styling goes, this is where the batch table comes in. So these colors are based on the metadata that we included in the batch table. And it's really easy to set up and modify on the front end. That's another benefit of 3D tiles. In the entity system, a lot of that work had to be done on the back end. But now that we have the information in the 3D tiles, we can change these at runtime. So you simply specify what property of each feature or a cloud you want to change. In our case, it's the color. And you specify a list of conditions based on the variables that you include in the batch table. So in the first condition, for example, we're saying that if the lightning property is greater than equal to 4 for some cloud, then color that cloud purple. And we're doing something similar to show light, moderate, and heavy precipitation. So now on to flight planning. To aid in flight planning, we built a simple flight plan entry system on top of Cesium. A pilot can enter what their desired flight path is, and then we check their flight path for collision with any clouds. If there's no collision with the clouds between 2 waypoints, or if you are in the VFR conditions, we draw a blue line. But if you're in the IFR conditions, then we draw a red dashed line. And we also draw a 3D corridor along the path where the exact collision is, so the user can amend their flight path to avoid running into that problematic area. Now, this is a top-down visualization, and it's helpful for planning. But if a pilot really wants to see close up what the weather picture is, they can use the real-time flight view. And that looks like something like this. So in this flight view, the plane actually flies along the flight path, and the weather will update based on the time in flight. Since with our data, we have up to 18 hours ahead of forecast. So at the hour mark, the tile set is switched to one that is valid for the next hour. So the user is seeing information that's accurate to their flight time. Initially, the mandate from the FAA was to simply have the weather shown for the current situation and just to keep that static and make decisions based on that. But with 3D tiles, we're able to instantly swap the tile sets and show the actual forecast. So in conclusion, with this new rendering technology, we've been able to demonstrate real-time 3D visualization of weather elements such as clouds. And while the area we see covered here is just the continental United States, there's no defined limit on how big this data set could be. It could cover the whole globe, and 3D tiles would be the way to go in displaying that, since it doesn't hold the whole data set in memory. The only thing it loads and renders and processes are the stuff that you're actually looking at. So from this process, there's a few things I learned that I'd like to share with you. A few takeaways for people who might be trying to do something similar. So if your work involves working with massive geospatial data sets, and by massive, I mean, it had to be more than 1 million data points. Anything less than that, the entity system can't handle. So if you're working with massive geospatial data sets, 3D tiles and cesium are a great option. Odds are that the cesium ion service will automatically generate the 3D tile set for you. It has support for a great number of geospatial data formats. And once it generates it, it's as simple as drag and drop. For displaying 3D data on the web, use the GLTF format. A lot of websites like Sketchfab, Google, and even Facebook, that's what they use. And it's really fast in downloading your data and displaying it efficiently on mobile too. And works great with any rendering engine that uses WebGL. If you do have custom geospatial information and you want to create a 3D tile pipeline, my recommendation would be to create it as generalized as possible. This is a principle in general software development, but you want your software to be broken up into modules that are interoperable. So if you're creating custom geometry in GLTF, keep that code separate from the code that's doing the spatial subdivision for your 3D tiles. That way you'll be able to reuse a lot of code in future projects. And for really large data sets, using the right spatial data structure really matters, especially if you have a model in which there's lots of LOD switching. And it can really make the difference between having a smooth transition as you zoom in versus a really choppy one. And lastly, I guess this is a principle for any sort of software when you're working with large data, but make heavy use of concurrency and design for concurrency from the very beginning. So with geospatial data, there's so much potential for parallel computation on the GPU and the CPU. In our pipeline, for example, on the back end, we use multiprocessing for generating those I3DM files, since it's an IO operation, and that's something that scales really well with the number of CPU cores you have. And we're leveraging the GPU to do mathematical computations on those 2D grids that you saw. And on the front end, we use web workers to check for collisions between the flight path and the clouds, so that the main UI thread is not blocking up the normal operation of the website. And that's about it for me about Flight Profiler. I will now open it up to any questions that you guys have.
So if anyone has, can you hear us, Sanjeet?
Yeah, I can hear you.
If anyone has any questions, give me the mic. So is this some of this tool? They have it up on the web now? I wasn't clear. Is it? Oh yeah, I'll scratch my question.
Sanjeet, thank you very much. It's probably not a very smart question in a certain way, but I'm just curious, this is basically to be used for pre-flight planning, correct?
Right.
So the research challenge here is, I'm guessing, given that clouds change very quickly, pre-flight planning and cloud formations is not particularly a precise usage. However, for the research challenge related to how you're enabling the data the representation of that data, that's really the core of your project. Is that correct? Have I understood this?
And that is correct, yes. Our focus is on using this new technology to display this amount of data.
Okay, and I'm just wondering, have you applied any machine learning algorithms to this in order to simplify some of the processing of the information related to like any repeat structures that might be occurring? Have you been able to program any kind of learning into this model?
At the moment, no. This is purely an exercise in mathematical optimization. But as we move towards, so now that we have this data displayed and say a user, a pilot is encountering a cloud in some area, machine learning, the scope for machine learning would be in recommending an alternate path. So right. That's when machine learning and this sort of reinforced learning would come in handy. But at the moment, no, there is no machine learning being done here.
You're really focused on simply the data representation at the moment.
Right, right.
Yeah, I mean, I can see applications, but it's going to take a while before we're able to process quite that much information in real time, I'm guessing. But
right.
The use of the 3D is actually has great potential in this particular area. Thanks for sharing.
Yeah, thank you for your question.
All right, here's another question.
Yeah, at the scale of the problem you're working on, is the curvature of the Earth a factor, and does 3D tiles accommodate that?
Yeah, so 3D tiles is designed for using a web engine, and it's an open spec. So this could be implemented in something like Unity and otherwise too. But when you're working with this data, it's really important to understand the difference between a Cartesian coordinate, which is your XYZ, and your cartographic, which are your lat long altitude. So you have to be really careful when you're working with this data to, and this is something I struggled with a lot because I didn't understand what the data represented, what the actual coordinates were. And when you actually encode your data into 3D tiles, you'll be using a Cartesian coordinate, so your XYZ. But the cesium engine does a great job in accommodating for that curvature. So if your camera moves away from the curvature and your tiles are behind that viewport, the actual globe is a physical volume. And it can check for collision there, and it can unload those tiles that are not in the view from memory. So that's not something that's a part of 3D tiles. It's part of the engine that implements 3D tiles, which in our case is cesium. I hope that answered your question.
Yeah. All right. Okay, good. I don't see any other questions. So thank you, Sanjeet. I'm sorry you weren't able to join us down here in person today.
That's okay. Thank you all for your time. I hope you have a great conference.
All right, excellent.